So this is a design builder panel. Okay, so we will see how the external CFD analysis is being done in a design builder solver. Just before the starting of the discussion. Okay. So first, today's discussion is about the external CFD analysis. First, we will see the example given. Okay, so in here it is the condition is given as pendulum. No problem. Let it be like that only. Okay. So we will go to the solver. So when you are entering the design builder, some sample problems will be given inside. Okay, so you can go through that and you can take that example and you can go through that and you can learn. So these are like tutorials. Okay, so these are like tutorials. So from that you can learn. Okay, yeah. So I got it. I got the building. So this is the tutorial what they have given for external flow CFD analysis. First, we will see this problem. After that, I will show one more problem also. Okay. So this is the building. Okay. So this is the building which it has been constructed. Okay. It's a simple building. Okay. So it is not created by me. So it is already given. Okay. It is already given in the solver itself. If you enter into the design builder solver, so you can see this building. Okay. So when you want to go for external analysis, you should understand. I told there is a hierarchy in the building data. Okay, there is a hierarchy. I told bottom most you will be having the wall. In the wall also you will be having a few divisions. Okay, so you will be having openings. Okay, so just 1 minute. It is taking a little bit of time. Okay, so you can see in the wall you will be having windows. Okay, and you will be having the external wall, and after that you will be having the walls. So I told all the walls, roof, and ground floor put together, it will form a zone or room, and this zone, okay, a group of rooms put together, it will form a floor. But here, just we are presenting only one building, okay, a small building, okay. So if you want to do the external CFD analysis, you have to start with the site. So this is site. Already I told you. First you will be having site, and after that you will be having the building, and after that you will be having the floors, and after in the floors you will be having the rooms. Okay. So that means it is sufficient. Okay. So for better understanding, I'll close everything. You should not even for doing external analysis, you should not even do it in building. You have to go to the site. Okay, I have to select the site. So it is untitled site, no problem. Okay, if you are going for site, so you will see three partitions will be there. Okay, so if I am coming for building only, I'll be having all these components. Okay, separate components will be there. If I'm going for site, only these three things will be there. Okay, in that I have to go. Okay, inside. Okay, so there. In the site location. Okay, so in the site location, the latitude, longitude, this is for Bintulu, that is a Malaysia condition. So let it be like that only. And you can tell about the elevation, sea level, exposure, site orientation also it is given. So orientation is with respect to north. Okay, so I'm giving it is 0 with respect to north. So that means the building is in the north direction. Okay. So that information we have to give it because we are going to do a CFD analysis. Okay, site orientation I have to give it. Okay, okay. So then now already it is there default whatever it is there. I'm taking it as 0. Let us go and see. Okay, so this is a simple CFD analysis for a building. Flow over a building. Okay, it is not inside the building. It is flow over a building. So that is what I called as a CFD analysis. So from here, so here you can see only 3 tabs will be there here, but at the bottom I will be having a CFD tab. Okay, so when I press the CFD tab, I have this external CFD analysis. So I have the grid details. Okay, so I have the grid details, and I have the velocity details. Okay, so velocity means what is the velocity with which the wind is blowing over the building, and also you should know if wind is blowing, it will be flowing in a particular direction. So what is the direction with which the wind is blowing? Okay, so I am taking it is a 45 degree. Okay, from the north. So it is a 40 inclined at 45 degree towards from the north. Okay, so in the exposure, yeah, I have a open country, suburban, and urban. So you know the flow pattern will be different for open country, suburban, and urban. Urban is like city. Okay, suburban is between a village and the city. Open country is for like village. Okay, so I take okay, so I take as suburban. Okay, then I'm giving the factors. So what is the site domain factors? Because here you are having a building, the mesh will be done over the building. Just now we are going to see. Okay, mesh will be done over the building. What should be the height for which the mesh has to be done? Okay, so that is what it will be given here. Okay, so it is given as 3. Okay, so I can change it. Okay, so I can change it as 6. I am doubling the domain. Okay, so I am doubling the domain. What is the domain in the CFD? That in CFD the domain is R only. Okay, the domain is R only. So now I am giving now I am doubling the domain size. Okay, so I am saying it is okay. Okay, so now okay, so now I think we have to start the CFD calculation. Okay, we have to solve this CFD calculation. So the building is not visible. Okay, 1 minute. The building is not visible. No problem. We will start the CFD calculation. Okay, so we will start the CFD calculation. So it is like a building is there, over that domain is there. For that domain only, it is the air domain. Okay, the air is the fluid, that is a fluid domain that we are meshing. I will show you the meshing details. I will show you. Okay, so this is how we will be running the solver. Okay, so we'll be running the solver. So first, it is a new CFD analysis. So whether what type of turbulence modeling we are using, so that we have to use. We will discuss all these things. We will discuss. Okay, and what discretization scheme you are using. Okay, for convection. Note the point. Okay, I'm telling some word called as convection. So that also we will be studying today. Okay, I'm talking what is the maximum number of iterations. Okay, so that also we will be discussing. What are all the initial conditions? So initial condition means it is not usually CFD. We are not doing a transient analysis. It is steady state analysis only. Then why we are having initial condition? So it is actually an iterative solution. When you are going for an iterative solution, you will be giving the initial values. Yesterday we have seen about a Gauss-Seidel procedure. So in the Gauss-Seidel procedure, I told that for solving the problem, we will be going with the first set of values, Gus values. Gauss-Seidel, it is actually a Gus and correct procedure. First, we will be having a Gus values. So those values only we are giving. We are giving these values throughout the domain. Okay, we are giving these values throughout the domain. Okay, so you can monitor. Okay, so we can monitor the cell value. Okay, inside the domain. So that means at some point you can find out what will be the monitor the velocity. As the solution is as the computer is solving the solution, you can find out what is the velocity. So if the velocity, so that is what is given here. Okay. So initially you will find that there will be fluctuation in the velocity because you are Gus and correcting. Okay. So in the Gus and correcting, in the first state itself, you will not get the correct value. So you so initially the residue or the deviation will be more, and after that it will be reducing and it will become constant. So that is what we will be having. Okay, and so that is how cell monitor. Default one monitor will be there. If at all you want to have a monitor extra, okay, so that we can do it. So that we will do it. Okay, and the next discussion will do that. And what is the residue? Okay, so this is called residue graph. So you know, for a flow analysis, what are all the equations we will be solving? In flow analysis, we will be solving the mass equation, that is continuity equation, x momentum equation, y momentum equation, and z momentum equation. So why we are solving this in a flow analysis? it is sufficient for us if you have pressure and velocity distribution. So for pressure we have continuity equation. For the momentum, I have x velocity, z velocity, y velocity. Okay, x velocity, z velocity, and y velocity is there. So three momentum equations and one continuity equation is there. So that means 4 variables I have to get. But you know, velocity is a vector, so it will have 3-dimensional form. So it is a, you can have the velocity value. Okay, so what is the component of velocity? Okay, what is the component of velocity? So that you can have it in the plot. So totally you will be getting 2 plots. Okay, so one is x plot and one is velocity plot and another is pressure plot. In the specialized CFD solvers, okay, so you can get individually what is x velocity, what is y velocity, what is z velocity. So you can get it separately also. So that means if you are solving 4 equations, you will get 4 plots. So regarding this also, we will be studying in detail. So why I am doing this sample, because we are going to discuss these components. At that point, you should understand the importance of these components. Okay, so that is why I am going in the beginning. So you have to suppose if you are enabling, you are using here you can see when I enable here this equation is included. So if you are going for a turbulent model, that is a k epsilon model, so that means that equation also it will be getting added. Like how we are having equation for continuity, x momentum, y momentum, z momentum. Likewise, we will be having equations for turbulent kinetic energy and the turbulent dissipation also. Okay, so that is what I am having here. So when I solve all these things, so I'll be getting the residues. So we don't want a higher residue. Okay, so what is the residue? So left hand side you will have the equation, right hand side you will be having 0. So when you are using guess and correct procedure, so when you are giving the first value, the residue will be very much higher. Okay, so as I am marching towards the correct solution, this residue value will be decreasing. So finally the residue should become 0, but there is no definition for 0. Okay, so 0, one can say that 10 power minus 4 as 0, other can say 10 power minus 10 as 0, another one can say 10 power minus 20 as 0, another one can say 10 power minus 100 also as 0. So that means you have to define the 0 for the computer. Okay, so that is called the convergence criteria. So here also that is what is given here. Okay, so that is what is given here. So that means if it is less than 10 power minus 3, okay, then you can say that the solution is converged. So like that only the solution process will be continued. So what you are doing, we are using the guess and correct procedure only. Okay, so we will be giving the for the domain whatever we have taken. So we will be giving the guess values and then we will be correcting the values. Okay, so now this is how the solver will be working. Let us start. Okay, so let us start let us start the discussion. Okay, so let us start the solving the problem. So here you can see now it will start solving the problem. Okay, now it will take time. Okay, so let it proceed. I think you can see now it has started. So there is a small so we will proceed. Okay, we will proceed with our discussion. We will go for our presentation. So let us come back to see how the solution is converged and how to see the plots. Okay. Okay. So 1 minute. Let me see how many of you are there. Okay, 30 of you are there. Okay, very good. Now I will. We will go with the discussion. Okay. 1 minute. So I will go with the presentation. Okay. So before that, okay. Now the solution is going. Okay. So let us see after converged solution when it is converging, we will see. So till then, we will proceed with our presentation. So today we are going to discuss about the basic of computational fluid dynamics. We are going to the next system further. Okay. So previously we have gone for one step. So now we are going for the next step further. So it is external CFD analysis. Okay. So what is external CFD analysis? If you are having buildings like this, okay. So what will be, and if the air is flowing over the building, okay. If the air is flowing over the building, so that is called external CFD analysis. Okay. So that is called external CFD analysis. So Uh, Today we are going to discuss about how we do the external CFD flow analysis. That is why I've taken that example and I'm doing. I'll be solving one more example also. Okay, till that the solution is completed. Okay, so it is proceeding in the solution. So we will continue our discussion on the basics of computational fluid dynamics. So whenever you are doing external flow analysis in the building, so you can come across this type of flows. Okay, so here you can see because of the building, the airflow is getting blocked. Okay, and the rear side you will be having wakes and the circulations will be there. So similar, whenever air is flowing over a building, on the rear side of the building we will be having wakes or circulations. So the what is the speciality about the wakes? These wakes will be having a low energy. Both the pressure and the velocity will be less at that region. Okay, so that means you know about the atmospheric pressure. So because of the flow, there will be a small vacuum. Okay, it is not perfect vacuum, so there will be a small vacuum. Less than atmospheric pressure will be there on the rear side. Okay, and a lot of circulations also will be there because of this wake. And whenever the flow is there over the building, on the front side of the building there will be a positive pressure. On the rear side of the building, I will be having a negative pressure. Okay, so that also we have to see. Okay, so these are the things which we will be studying. Okay, so when so mostly we will be checking the airflow pattern. So we have to check the airflow pattern in a building, because a good airflow pattern in the building results in a good circulation of air. Okay, whether it is conditioned or non-conditioned, it will result in a good air circulation for every occupants in the building. So it is good. Okay, so for that we do the external flow analysis. So then what is the internal flow analysis? In the internal flow analysis, we will be going inside the building and we will be doing the CFD analysis. For example, if there is a air conditioner inside the building, we will be discussing about the flow distribution. Okay, whether the uniform distribution, flow distribution is there for conditioned air inside the room. So that we will be discussing. Okay, so this is how. Okay, so this is how the patterns will be there for external CFD simulation. So yeah, it will be looking very good. Okay, so that you can see. Okay, and but what is that we have to understand is that what is the effect of this flow, okay, on the buildings. Okay, so that is what we have to understand. And you should understand that the wind flow will not be constant throughout the year. Okay, wind flow will not be constant throughout the year. So wind flow direction will be varying at a different time of the year. So that means if you are at a particular location, you can do simulation and you can find out what will be the flow pattern in the building and what will be effect on the occupants. Okay, what will be the effects on the building and occupants. Okay, sometimes if you are having a high rise building, so even you can find out what will be the force wind force on the building. Okay, so what is the effect? Some you can even you can go for extreme conditions. Okay, so for example, if you are having a cyclone, okay, so wind velocity is very much higher. So then you will be interested into finding out what will be the effect of the wind on the building. What is the force of the wind on the building? Okay, so we should understand the loading by the wind. Okay, it will be like a cantilever. Okay, with the distributed load. So that is how we have to make the analysis, and we have to find out whether the building will be safe in the or the structure will be safe in the building. So that also it can be done. Okay, so that it can also it can be done. Okay, but similarly when you are planning the cities or if you are planning for any township, so you can put the building nicely in a particular location, so that that whole location will be well ventilated. Okay, so that will be useful for planning the buildings. Okay, in a town or in a village. Okay, so okay, so in internal CFD, again it is like this. So you will be having the domain. Okay, so you will be having the domain like this. So inside we will be doing. Okay, so we will be giving a external excitation, like we will be giving the supply area and we will be taking the return area. So what will be the flow pattern because of these loads and everything? What will be the flow pattern inside the building? So that is what we will be finding out. Okay, so that is called internal CFD. So regarding internal CFD in detail, we are going to study tomorrow. Okay, so today we will be studying about the external CFD, and side by side the theory of CFD also we are going to study. Okay, okay. So what is CFD? Okay, so yesterday we have seen what is the CFD. CFD is the term that is used for a family of numerical methods for calculating the temperature, velocity, and other fluid properties toward the region. Okay, or CFD, that is the name what we are given for the CFD. Okay, so family of numerical methods used for different types of equations. Okay, but the CFD you can take it in the other way also. CFD is the process of dividing the arbitrary shaped domain into number of regular shaped subdomains called as meshes. Okay, and for each mesh I will be having a governing differential equation, and this governing differential equation will be converted into algebraic equation. Okay, and these algebraic equations will be solved simultaneously. The equations will be in the form of matrix, and we will be solving this equation simultaneously for getting the solution. Okay, and what is the domain in CFD? The domain is a fluid. Okay, so here also we are considering the domain. The domain is a fluid. Okay, so that is what we are considering. What will be the next external excitation? For example, if you flow over a building or external analysis, what will be the excitation? The velocity of the wind. Okay, the velocity of the wind will be the external excitation. Okay, so because of that velocity under pressure, so there will be a flow pattern around the building. The flow pattern around the building is the response of the building. Okay, so the external excitation is the velocity. Velocity is the boundary condition. Okay, so that is what. So the plots and all what we are giving. So seeing, those are all called as the response of the building. Okay, that is the response of the domain to the external excitation. Domain is the CFD. Okay, domain is the CFD domain. That is air. So what is the response of the air to the external excitation? Okay. For example, if you are going for internal CFD analysis, so you are going into a conditioned room. So what is your domain? It is a fluid. For what is the response of this fluid for the external excitation? Just now you have seen it. What is the response of this building? External excitation means to the flow, air inlet, air outlet. So loads coming into the building, solar load, everything entering into the building. Loads which are persisting inside the building. Okay. So for example, if it is a human load, if it is a equipment load, if it is a so like that. Okay. So all these things. Okay. If you are doing, if you are giving all these things and you are trying to find out the response of the domain. So what are all the responses you can find? Responses of the domain, responses of the air to these external excitations. So the responses, possible responses are, you can find out the velocity distribution, you can find out the pressure distribution, you can find out the temperature distribution. Okay, so these are all the responses of the domain to the external excitation, which are all the boundary conditions. Okay, so that is how we have to understand. Okay, so what is CFD? So yesterday I have defined it differently. Okay, so yesterday I defined the CFD as a response of a domain to external excitation. That is okay. I told the domain will we are dividing into number of grid points. So when you are going for finite difference method, we divide the domain into number of grid points. When you are going for a finite volume method, we are dividing the domain into number of volumes. Okay, regular shaped subdomain called as volumes. Okay, so that means that volumes are called as the meshes. Okay, so that volume is called as mesh. So the main points to remember is the fluid. Okay, fluid is the domain. In CFD, fluid is the domain. So we will be dividing the fluid into number of regular shaped subdomain mesh. That mesh is also fluid. So for this mesh, for each mesh, I am having fluid flow equations. So these fluid flow equations, we are calling it as the physics of the problem. Already I told you the possible physics of the problem in air conditioning application will be, so pressure distribution or finding the pressure, continuity equation, it is one physics. From that we find the pressure. Okay, then momentum equation. So the physics is momentum. From that we are finding the velocity distribution, x velocity, y velocity, and z velocity distribution. Then we are finding out what will be the temperature distribution. So that is the temperature distribution is the response of the building to the external response of the fluid domain. Okay, energy response of the fluid domain to the external excitation means to the external thermal conditions. Okay, so these are all the possible responses. Okay, and we should know that these things are dependent on the response depends on the fluid properties. So that means for all the simulations we will be giving the fluid properties. Like in the energy simulation software, we have given the properties of solid, like building construction material, glass material, all this thermal properties corresponding to that we have given. Similarly, if you are going for CFD, you will be giving all the properties corresponding to flow. For example, if it is flow, like what we are doing today, without any energy application, without any thermal application. So today you are doing external flow. There we consider the flow is isothermal, or we are not considering the temperature. Okay, we are just finding out what is the pressure distribution and velocity distribution. So those type of problem, it is called as a flow problem. So for this flow problem, we will be taking for this type of flow problem. So we will be taking the properties. What are all the properties we will be taking? Density and viscosity only. So these are all the two main properties which will be there in the fluid flow equations. But when you are going for same CFD analysis, if you are doing it for internal analysis, so then you will be doing air conditioning and temperature distribution. So in the air conditioning temperature distribution, inside the room, you want to find out the temperature distribution. So that means you will be solving the energy equation also. In external CFD analysis, you will not be solving the energy equation. Just now we have seen there was no temperature equation or energy equation. Okay, but when you are going for internal CFD analysis, definitely we will be solving the energy equation. So inside that we will be solving the energy equation. So in the energy equation means what are all the properties pertaining to energy equation. So that also we have to give. So for example, I have to give the thermal conductivity, specific heat. Okay, so these are all the thermal properties. Okay, density. So those things also we will be giving. So similarly, if I'm adding one more equation, for example, mass transfer equation, if I'm adding, that property also I have to give. Okay, for example, you want to find out what will be the water vapor distribution inside the room. Till now, we don't have solvers for modeling this. Okay, so you are interested in introducing the water vapor distribution inside the room. So that means water vapor is a species, then air will be a species. So then you have to do modeling for this too. Air, water vapor, everything you have to do the modeling. So that means then I have to give the properties of water vapor also. Okay. So that means mass transfer properties I have to give. What is the diffusion property of water vapor in air? That I have to give. Similarly, air in water vapor. So what is the diffusion coefficient of air in water vapor? So mass transfer properties. So what is that you are understanding? So that means if I'm adding one more every equation, that means I have to add the corresponding property library also. That is what you have to understand. Similarly, for each physics, I will be getting one plot. So if for each equation, I will be getting one plot. In other words, for each physics, I will be getting one plot. So that is what we have to understand. Okay. So what are the steps in using a commercial CFD software? Okay. So first we will be going for modeling. So now also we are first there was a building. So over the building that we just put a box. Okay. So that is the airflow domain. We will see that. So then we have cut that domain. Okay. So then we give the we measured that domain. And after that, we are given the boundary condition, velocity, orientation, everything we are given. And then after that, we in the post processing, we are just cutting the domain. And after that, we are post processing. Okay, we are seeing the domain, and then from that, we get the velocity information and as well as the pressure information. So and that is what we are doing. So that means in any CFD analysis, first we have to model the domain. Okay, model the domain means we have to draw the domain. Okay. So using your preprocessor, that can be any solver. Okay, so you can do. So now here you can see in Design Builder, I can do it with the Design Builder preprocessor itself. Okay, so now I have to model that. I have to draw the fluid. Okay, and after that, what I have to do, I have to mesh it. So what is the meshing? So process of dividing the domain into number of regular shaped subdomains. Okay, so all this subdomains means meshes. So it will be regular shaped. So it can be triangular shape, or I'm sorry, it can be a tetrahedral shape, it can be a prism shape, it can be a pyramid shape, but it will be a regular shape. Okay, so we will be dividing these domains into a regular hexahedron, it can be a pyramid, okay, prism. So all these things, shapes you can have it. So these are all regular shaped subdomains. Okay. And after that, we will be giving the boundary conditions. So, you know, if you go for a solver, you give that. Now, just now also you would have watched it. So, I've taken the domain, I have given the outer domain information, then I have given the default mesh information, and after that, I have given the boundary condition. That is velocity and the direction I have given. and now I am running the solver. So after the running the solver, it is called a processor. Okay, the solver is called as processor. Okay, and after that, what I have to do? I have to after convergence, I have to stop that, and I have to do the post processing. So that means I have to stop the thing. Okay, after convergence. So if it is converged, I have to stop, and after that, I have to do the post processing. Okay, so post processing means I have to see the velocity plot, pressure plot, or the velocity vector and the pressure vector. All these informations you can see. Okay, so this is the basics. So you will be having, and don't think that this basics is only for our discussion today. This is applicable for general CFD, general FE also, finite element analysis also, the same thing you will be doing. So there you will be doing it for a structural problem. There also you will be first drawing that, and after that you will be meshing that, and you will be giving the boundary condition. Then you will be solving it, and you will be going for post processing. So in post processing you can get the plots. Okay, so the plots will be like contour plots, vector plots. Okay, or sometimes if you are doing a transient problem, it can be a time dependent contour plot. So that is also possible. Okay, so time dependent informations you can obtain by a transient analysis. Okay, so that is the structure of the equations. So now again we will go back, okay, to see whether the equation has converged or not. Okay, so I think okay, so now you can see here, now the residues are decreasing. Okay, residues are decreasing. Now I told the x velocity is oscillating. Okay, initially the error is there is large variation in the x velocities. Then you can see now it is the fluctuation is reducing, and it is now the amplitude of the fluctuation is reducing. After that, this will go constant. Okay, that means till now it is not converged. Okay, so let us wait till this horizontal line will be there. So till we get that horizontal line, let us wait. So for that, this has to come down. Okay, like this. So let us wait. Okay, so we will proceed with our discussion till then. Okay. Okay. So they are here. So we were here only. Okay. So now the general CFD solver. So this is how we will be having preprocessor. What is the purpose of a preprocessor? I will be having it. I can create a geometry. I can generate mesh. Okay. And giving the material and the boundary conditions mostly we will be doing in the solver only. Okay. But okay, this has to be given in the solver only. Okay. But where you will be giving to the geometry only. So in the geometry we will be mentioning this is fluid. For this fluid, this is the property. So that is how we will be giving. Similarly, boundary condition, it is external excitation. So that means at this point, this is at the entry, this is the velocity. At the wall, this is the temperature. At the exit, this is the velocity. So I have to give that information. Then only I can find the solution. So that is boundary condition. So what will be there inside the solver? Okay, so in the solver, so you will be having all these equations. Okay, but all these equations, while solving, it will be in the algebraic form. So already I told you, so it will not be in PDE form. So this PDE will be converted into algebraic equation. Yesterday we have seen that if it is a one-dimensional equation or a two-dimensional equation, how the equation is converted into algebraic equation. Yesterday we have seen that. Okay, so all these equations, okay, mass equation, momentum equation, energy equation, equation of state, mostly in compressible flow we will be using it. Okay, other supporting models. Okay, so all these things we will be having in our these are all the transport equations, or in other words, these are all the physics. Okay, equations are the physics of the problem. Okay, so these are all the physics of the problem. Okay, and we may be having some supporting models like a turbulence model, combustion models, radiation models, and other thing. But this is for a general purpose CFD solver for buildings. Okay, so we may not have the radiation. We may be having radiation. Combustion we may not be having. Turbulence we'll have only simple models in turbulence. Okay, so that's how. Okay, so that's how there will be difference. And how the solver is going to solve my problem? Okay, so by iterative procedure or guess and correct procedure. So I am going to have the series of linear algebraic equations. How many number of nodes are there? How many number of meshes are there? So many number of linear algebraic equations will be there. So I am going to solve these linear algebraic equations by mostly in CFD we will be going by guess and correct procedure or iterative procedure. So in the guess and correct procedure or iterative procedure, first I'll be going with the initial solution. It is not initial condition, initial solution. That is, with initial guess we will be going. So that is called initialization. Okay, and after that, every step it will be trying to collect. So yesterday we have seen two methods. One is gas Jacobi and another one is Gauss Seidel. So there we have found that we go with a every iteration we go with a guess set and then corrected set. So that means guess set. So the next iteration, the corrected set will become guess set. So like that, we will be using the guess set and corrected set. Corrected set will become guess set, and again we will be doing the correction. So in that process, we will find that our residue will be decreasing. Just now we have seen in the solver, the residue is decreasing because it is going in the correct direction. So always it will not be happening. There are sometimes when residue will be increasing also. So just now you have seen in the solver, the residue is moving down. Okay, so that means it is a good news for us. It is also possible because of the bad meshing, or because of the bad formulation of the problem, or because of a bad boundary condition. So it is possible that the residue can increase with respect to number of iterations. So that is also possible. That means it is going in the wrong direction. So technically it is called as a divergence. Okay, when the residue is decreasing with respect to iteration, so technically it is called as convergence. So that means you are getting convergence. So if your residue is diverging, okay, so that means it is a bad news for you. So that means you have to redo the problem. Okay, so you have to redo the problem. You have to check the problem statement. Okay, boundary condition, mesh, everything you have to check it. Okay, so that is how you will be having. So that means you will be having initial gas values. And okay, so after that, while the solution is running, you have to monitor the solution. Then only you will know whether it is converging or diverging. Now I have gone there, I am seeing, okay, all the residues are decreasing with respect to iteration. So that means, okay, good news. I understand that the problem is solving in the correct direction. I know that after some time I will be getting the solution. And also it is possible that it may go in the opposite direction also. So that means the solution, the residue may increase with respect to number of iterations. You can know only if you able to see the plot. So that means you have to monitor the solution. Okay, you have to monitor the solution. So that means if you are able to see only, you can stop. Otherwise, what will happen? The solution, if you are not monitoring the solution, so the solution will be running for 2 or 3 hours. After that, you will find that you are not getting the thing. Then if you go inside and see, you will find that the residue is diverging. So for that purpose only, for monitoring the solution, it is an important task. Okay. So you have to give the initial condition. Now also when I was solving the problem, I was giving the initial condition. And after that, I have to do the solution control. I will tell you what is solution control. You have to monitor the solution, and you have to see the convergence criteria also. What is convergence criteria? I told zero definition. So residue should become 0. That means your solution is converged. Your algebraic equations are converged. If your residue is not equal to 0, okay. So if your residue is not equal to 0, or if your residue is more, that means the solution has not converged. And also I told residue will not be equal to 0. I have to define 0. So that the process of defining 0, so that is called as convergence criteria. So what is your criteria for convergence? So 10 power minus 3 can be your criteria for convergence. You will get the solution faster. Residue will reach 10 power minus 3 faster. But you have to see whether your parameter has stabilized. Now you have seen two things. So when you are going for the thing, so we are seeing we are just seeing two things. So one is we are seeing residue is decreasing. Okay, residue is decreasing. The other thing is you have to watch the parameter also. Parameter also it should be stabilized. Sometimes it is possible that the residue might have reached the 10 power minus 3, but still oscillation will be there inside velocity. But that is not possible. That means convergence has not been attained. Okay, so both the things you have to see. You have to monitor the solution as well as you have to monitor the residue. So that is very important. Okay. Okay. So after completing the solution, we will be doing the post processing. In that, we will be getting contour plot, velocity vectors, XY plot, and all these plots we will be getting. Okay, fine. So now we are going to the most important and interesting portion of the transport equation. So far, we have seen only energy transport equation. Okay, so in detail, we have seen about the energy transport equation. So now we have to discuss about the total transport equations. Okay, so that is we have to discuss about all the equations. So why you have to know, if you don't know about the equations, so it is difficult. It is very difficult for you to understand CFD. Okay, so let us spend some time on the equation. Okay, so let us spend some time on the equations. We will go further. Just 1 minute. Okay, we'll go to the board. Just few minutes only. Okay, so it is not going to take a very long time. Okay. Yeah, let us pick the, okay, let us pick the slides. Okay, so let us not do it for all the slides. Okay, so I will pick only 4 slides today. Okay, everyone should be happy because I'm not doing everything. Okay, so okay, okay, 1 minute, there is something is there. I will drop it. Okay, yeah, we will go to the next step further in equation also. Okay, so we have learned about the equations. So we will go to the next step further in equation also. Okay, so first we will yesterday we have seen in a transport equation. So what are all the things I will be having? What are all the possible things I will be having? So I told that we'll be having transient. Okay, so 1 minute. So I'll be having the transient term. Okay, so this term I told it is transient term. So yesterday we have discussed the transients of the energy equation alone. But you should understand that the transients is there for all the equations. That means for continuity, 3 momentum, x momentum, y momentum, z momentum, as well as for energy, as well as for even species concentration also, I have this. Okay, so that means I have this thing. Transients is there for all the equations. Okay, so I have to understand that transients is there for all the equations. Okay, so that is what we have to understand. So now I told the next term is the convection term. So this term is the convection term. So this is the general convection term. Okay, so general convection term. So now let us know about what are all these terms. Okay, so first, what is V? First, what is V? So V, it is the velocity vector, so which I can write it as Ui plus Vj plus Wk. Okay, so all these things are vector. Okay, so it is a 3-dimensional vector. So that means this is a 3-dimensional. Okay, velocity vector. Phi is the scalar. Okay, the scalar, it can be anything. Okay, so it can be anything. So if you consider, okay, so if you consider this, so this can be, if I phi is equal to 1, okay, then in this equation I will be getting the continuity equation. If phi is equal to u and this gamma, if it is viscosity, then I will be getting the x momentum equation. So similarly, if I put phi is equal to v, I will be, and this gamma is equal to dynamic viscosity, I'll be getting y momentum equations. If phi is equal to w and gamma is equal to dynamic viscosity, I'll be getting the c momentum equation. Similarly, if phi is h on the left hand side and t on the right hand side, okay, and gamma is equal to thermal conductivity, then I'm going to get the energy equation. If phi is equal to c, okay, on the left hand side, okay, on the right hand side, if gamma is equal to d, that is the diffusion mass transfer coefficient, I am going to all these equations are going to be the your equations for CFD. Why this is insisted? Because this will be easy for you. Okay, so this will be easy for you. So you need not memorize all the equations within this one equation itself. So everywhere you can do it. This equation is applicable for all the flow equations. Okay, so this equation is applicable for all the flow equations. Okay, so that is how I'm having. So now that means if I put phi is equal to 1, I will be getting continuity equation. If I put phi is equal to u, okay, and gamma is equal to dynamic viscosity x momentum equation. If phi is equal to b and gamma is equal to dynamic viscosity, I am going to get a y momentum equation. If phi is equal to w and gamma is equal to dynamic viscosity, I am going to get the z momentum equation. So similarly, if phi is equal to h on the left hand side, okay, and t on the right hand side, I am going to get energy equation. So that means it's very simple for you. It is very simple for you. Within one equation itself, you are able to get all the governing equations for fluid flow. So that is sweet news for you. Okay, so you need not remember all the equations. So then, what is divergence? Okay, what is del? Okay, del is an operator. Okay, so it is I can write that d by dou x j into dou by dou y plus k into dou by dou z. So that's that I can write. So it's an operator. Okay, and if I directly have this operator as del phi, it is called grade phi. So then if phi is the scalar, okay, phi is the scalar. If this operator is operating on this, so then naturally this will become a vector. Grade phi, okay, it is a vector, okay, and this vector, what is divergence? Divergence is like a del dot, so it is a dot product. So dot product you would have studied in the vector. So dot product will be between two vectors. The resultant will be scalar, okay. So del dot, so that means it is a del dot of del dot of, okay, I have it as gamma grad phi, okay, so I have it as grad phi. So grad phi is a vector. So del is a again vector. So I'm taking dot product of these two, okay. So the resultant will be the scalar, definitely. So that means all our equations, it is in the scalar transport form only, okay. Okay, so that is very good news for you. Next is what is del dot of? Divergence is del dot. Already I told you what is the divergence. Divergence is del dot. So if you don't understand, also you need not worry. I'll be putting these equations in the differential form. So that also you can understand very easily. Okay. So you can try to learn. Okay. So you can try to learn even if you are not understanding. So please don't worry. We will discuss this equation in the differential form also. Okay. Okay, so now del dot of rho v phi. So rho phi, all these are scalars. What is v? V is vector again. V is a vector. So v is a vector. So that means when I take dot product of these two, the resultant will be the scalar. Okay. Yesterday we have seen these terms. Okay. These terms we have seen yesterday. So all these terms. Okay. So all these terms. This term was a transient term. This is a convection term. This is diffusion term. And this is a source term. So all these things are in the short form. Okay, all these things are in the short form. Okay, and this one equation itself, I am going to. I'm sorry. And this one equation itself, I am going to get all the things. So that means all the equations I am going to use in CFD, it is going to be applicable with this one equation. So that is a good news for us. Okay, and so that is how it is going to applicable for us. Okay, so now I have applied. Okay, so that is in this equation. I put phi is equal to 1. And if you put phi is equal to 1, grade of 1, it will become 0. Okay, so that means this term will become 0. In a continuity equation, there will not be source term. Okay, because continuity equation we are applying for a single species. So we cannot say water is emerging in water because everything is water. Okay, so that means the presence of source in a single species, so it is not required. So that is how this also will not be there. This term also will not be there. So I'm having dou rho by dou t plus dou of rho is equal to 0. So this is a continuity equation, three-dimensional continuity equation in the vector form. Similarly, when I'm putting phi is equal to u. Okay, so that means here I'm having u. Here also I'm having u. Here phi was there. I'm having u, and here also dou of nu. Right hand side for gamma, I am writing dynamic viscosity. So that I am putting then grade U, grade of U. So similarly, y momentum, I am having this equation. I am putting phi is equal to V, and your gamma is nu. I am getting y momentum equation. So in the z momentum equation, I am putting phi is equal to W, small w, and dynamic viscosity as nu. So I am getting this, and in the energy equation, okay. So I think here I have to put H. So it is given in the form of internal energy. No problem. I can write this as H also. Left hand side. Right hand side I have div K grad T. Okay. And I have extra terms also. When I go to energy equation, so I will be having viscous dissipation term, and I have a pressure volume energy also involved. So these two terms will come extra. But usually in calculations we don't take this. In incompressible flow calculations we don't take this. No problem. Then source. This equation we have seen yesterday. Okay, so I explained this equation yesterday. Okay, and please don't think that this will be there only for continuity, momentum, energy. So in the same form, we will be having a turbulent kinetic energy also, and even a dissipation rate also. So in general, for flow, what is that I have to understand? For flow, in general, okay, the properties will be transported. So properties will be transported by two processes. Yesterday we have seen by diffusion process and the convection process. Diffusion process means velocity is, if there is no velocity, a diffusion will be there. Okay, that means it is molecular transported. Okay, and if convection is there, velocity is there, convection will be there definitely. So that is how you have to understand. Okay, so now this I can expand. These equations I can expand. What is that means I can take this del. Okay, so I can take the del, and then I can expand this operators. So when I expand this operators, it is appearing in the very sweet form. All the equations are appearing in the very sweet form. The best thing in this is it is very highly structured, and it is very easy for you to understand. Okay, so here this is the all the equations. These are all the equations that are there present in the CFD. Okay, so these are all the only equations that will be there present in the CFD. Okay, but if there are there may be some reaction flow and other things. So those are all like extra equations that will be there. But basically, most of the time we will be using these equations only. Okay, so hope this is visible for everyone. Okay, so and now we will try to understand what are all the various terms. Okay, in this equation. Okay, so this is the general transport equation. So this is the general transportation. This is transient term. Yesterday we have seen that this is convection term. Okay, and this is diffusion term. Okay, and this is I'm sorry, my pen is not moving in the correct direction. Okay, I'm sorry. So I have the diffusion equation, convection equation, and this is the source term. I should not tell equation. This is terms. These are the diffusion term, and this is the convection term. And you can see the structure of the diffusion terms. So even momentum diffusion also it's having same structure. X momentum diffusion, Y momentum diffusion, Z momentum diffusion, and you can see the even the energy diffusion, that is conduction, having the same structure. Okay, and I have my mass transfer equations. So you can see that that is also having the same structure. Okay, so that is also having the same structure. So that means a diffusion, all the equations are having the same structure. All these equations are having the same structure. Similarly, convection also you can see. This is the general convection equation. And here, this is the convection of the momentum, X momentum, convection of Y momentum, convection of Z momentum, and this is energy, convection of energy, and convection of species. So all these are having same structure. So that means while solving also it will be very easy for you. For writing also it will be very easy for you. Just you remember this structure. Okay, that's just you remember this structure of the equation. So you can write all these equations very easily. So that is why I am writing all these things in the same form. This equation is very important. This one slide is very important. You understand this almost 25% to 30% of CFD problems you will understand. Okay. So first, yesterday we have seen this energy equation. So I told that this term is the transient term. If you remember, I told this transient term will be there only at the beginning, on the beginning of the. So, for example, if it's an air conditioner, if you are simulating the CFD of an air conditioner, so this transient term will be there only during the starting of the air conditioner. For example, initially the room will be at 30 degrees. So when I am switching on the air conditioner, the temperature will go from 30 degrees to 25 degrees. Okay. So that is the transience. Similarly, the air conditioner will be running. After the air conditioner runs, okay, I will some point of time I will be switching off the air conditioner. So that means the room will from 24 degrees again it will go to 30 degrees. So there also transience will be there. But when the air conditioner is running, okay, uh, uh, that point of time it will be running in steady state only. So that means whatever the energy supplied by the air conditioner and whatever the energy inside the room, so it will be in equilibrium. Okay, if there is no external load distribution at a higher level, so there will be in equilibrium. So that is what you will be having called as a steady state. Okay, so that means during steady state, this term will not be there. So that is what we have studied yesterday. Okay, so during steady state, we have seen that this term will not be there. So only during initial starting or transients, this will be there. Okay, this is with respect to energy. Now you can think about the momentum also. So you forget about the temperature which is carried by the room. Okay, so forget about the cooling of the room. So we will talk about the flow. When you are before the starting of your air conditioner, there will not be any flow in the room. Everywhere the velocity will be zero. Okay, and when you are switching on the air conditioner, much before the cooling, so you will get the flow inside the building. Okay, so that means you will get a velocity distribution inside the room. So that means near the air conditioner, you will be having a velocity, then it will be spreading and that velocity will be decreasing. Again, it will return back to the air conditioner. So that means there will be a flow distribution will be there. This flow distribution will be there much before the cooling of the room. If a room is much before the cooling of the room, this flow distribution will be there. So that means the steady state of the flow, it is reached much before the steady state of energy. That means we are having a different steady state. So we should not always think all the steady states will be same. Okay, it will not be same. Okay, energy steady state timing will be something different. Similarly, flow steady state timing will be something different. So that means when you are switching on the air conditioner, if the velocity distribution is arrived within a short span of time, okay, so that means from zero velocity, it will go to some velocity. In the air conditioner, the velocity may be around 2 meters per second. Okay, so from initially in off condition, throughout the room, you will be having zero velocity. That is one steady state. And after switched on, okay, immediately you will be having the flow distribution, maybe at that 2 meters per second, and the difference will be there distributed throughout the room. So that is called as flow transients. So these terms represents the flow transients. So this term represents the flow transients in the x direction. This term represents the flow direction in the y direction. This term represents the flow transients in the z direction. So similarly, if you are switching off the air conditioner, the flow pattern will be dropped. It will not be there. And it will not immediately drop. It will not be dropped immediately. Why? Because you know that when you are starting the fan also, when you are switching on the air conditioner, how you are getting the transients? It is because of the rotation of the fan. So the fan will not immediately go to that velocity. It will take some time, a small time it will take from going from zero velocity to that particular velocity. So that is called as a flow transients. So this term, okay, so that going from zero velocity to particular velocity, that is flow transients. So similarly, when you are switching off the air conditioner also, immediately the fan will not go to off. Because of inertia, it will rotate for some time. So because of that, your velocity also will be dropping slowly to zero velocity. So that means like energy, you will be having flow transients also at the beginning of starting the air conditioner. Similarly, while switching off the air conditioner. So in between, you will not be having flow transients. That means all these terms will become zero. Okay, so all these terms will become zero. While running, these terms will become zero. So now you should understand the significance of this term. So all this transient term will be there only at the starting and stopping, or you are shifting, your temperature is cutting on, switching off the air, your compressor is going off, compressor is coming on, your fan is going off, fan is coming on. So that point only this transients will be there. And this energy transients and flow transients will be independent. Why I am telling? Because you consider a air conditioner, your fan may be running, okay, but your compressor may go off. So that means your flow distribution will be there throughout the room, but your compressor is off. Because of that, there will be transients in the energy. So that is how this will be happening. And what about the concentration? Okay, what about the concentration? So for example, I'll give you one more example. Think that you are having inside the room, you are having a mosquito repellent. Okay, you are switching on the mosquito repellent. So the moment you switch on the mosquito repellent, you will not have the chemical, that mosquito repellent chemical distributed throughout the room immediately. It will take some time. Okay, so that means that is transience of the species. That is that chemical is mosquito repellent, whatever the chemical is there. So that is getting distributed. It will take some time for distribution of this species. So that is called as a species transient. Okay. Similarly, for going off also, it will take some time. For going off also, it will take some time. Okay. So that is the similarly, when I am switching off the mosquito repellent, what will happen? Immediately the smell will not go. It will take some time. Okay, it will take some time. So that means that there is a transience. So that means transience, increasing transience is also there, decreasing transient is also there. Okay, that means dou T by dou T may be positive, increasing, dou T by dou T negative, decreasing, dou C by dou T positive, increasing, dou C by dou T negative, decreasing. So that is the significance of the first term, whatever I have shown that here. Okay, and yesterday I told you about the source term. Okay, so in CFD, what is the role of the source term? In CFD, the source terms helps us for decreasing the complexity in the solution. Okay, for example, if I take the source term for the momentum. Okay, so suppose there is a momentum source inside the domain. Okay, if I am it will be difficult for us to modeling. For example, if you are asked to model air conditioner inside the room, so you know fan is a momentum source. So that means you will be having a evaporator inside, evaporator working inside the room, or indoor unit which is working. So inside that the fan will be there. If you want to do the simulation as per the CFD, then what should do? You have to model the fan, mesh the fan, and then you have to write. But you should know, if you are an expert in the CFD, you know that this process is very difficult. Modeling the fan blades and multiple fan blades and giving the boundary condition and running. If you are doing it separately, then it's okay. But if you are doing it in connection with all these processes, air conditioning process, it's very difficult. Doing the meshing itself, it will be a very big problem. Okay. So now the source terms will be coming for your help. So what you can do is that when you are modeling the CFD, okay, when you are modeling with the CFD, so what you can do that is, you know, what a fan will do, fan will create a velocity in particular direction. So you split that, okay, velocity into 3 components. Okay, so that means what? A fan will create a momentum in particular direction. Am I correct? So fluid will flow. Okay, that means it will flow with some momentum in particular direction. So what you have to do is you can split that momentum into, because even momentum also it is vector. The source also it can be a vector. So that means it will have the ith component, it will have jth component, and it will have kth component. So what you can do is, in the place where you are having the fan, wherever the flow is there, predominant direction, so you can split the momentum into 3. Okay, predominant direction, you give it in that particular direction, and whatever the direction it is coming, you can give it in the vector form. But you have to split it into 3 components. Okay, and then you have to give it. So what is happening is that you can model the room and you can mesh it, you can solve it. And this, whenever the flow is coming to that particular fan, the momentum fan portion or the fan domain, you are not going to mesh anything. You are not going to model the fan. You are not going to mesh the fan. Just you have to create a region of fan only. In that you can mention that this much is momentum is added in the x direction. This much momentum is given in the y direction. This much momentum is given in the z direction. So because of that, what happens? So it will reduce your complexity. So that means you have to give the momentum in the three directions. So that will be taken care. You will be getting the same result as the original fan was there in that position. Now, these three terms are helping us by reducing the complexity. Okay, and also I just now I told that if you are adding momentum to a particular zone, you can use these terms. Similarly, if you are removing momentum from the fluid, so that is also possible. For example, if you are making the fluid to pass through a filter, okay, so what will happen? Your velocity will come down. So actually, what is happening? So that is like a momentum sink. So what you have to do? You model the filter portion. Okay, to that you give that there is a drop in the velocity, or that there is a drop in momentum, negative. You give a negative source. Okay, so you divide it into three components because it is a momentum sink. So you divide that into three components. So x component you give negative value, y component you give negative value, z component you give the negative value. So that will solve your problem. So that means throughout your flow domain, wherever the components are there, for example, if you are modeling a strainer, okay, if you are modeling a strainer, filter, and other components which are there present, so there, though in those places, just you can give the in the source term, you can give it is a plus value, minus value. Automatically, the flow will take care. Okay, so that is the advantage. Okay, so for modeling the complicated components in the flow domain, these momentum terms will be coming for your help. What is the momentum source? So somewhere you are adding the momentum to the fluid. So that is called momentum source. The unit is in Newton per meter cube. This full equation, the unit is in Newton per meter cube. Okay. Even the momentum source also, it is in Newton per meter cube. So this is also Newton per meter cube. And yesterday I told this is in watt per meter cube. Okay, all are in meter cube only. Okay. Similarly, this is in moles per meter cube. Okay, concentration moles per meter cube. So all are in meter cube. So that will help us for volume integration when you are going for solving the problem. Okay. Okay. So now what about the yesterday I told you about the source of energy. You can take the air conditioner itself. So when I'm going for modeling the air conditioner, so now think from the energy perspective. So in the air conditioner, what will happen? In the air conditioner, there will be air from the hot air from the room. It will go to the air conditioner. So there it will lose its heat. Okay, underline lose its heat. Then it will go to low temperature, and then it will be entering into the room. Okay. So what is the meaning of losing its heat? So that means there is a heat sink. So that means it is a negative source in the energy. Okay. So what you have to do, instead of modeling the cooling coil, modeling the cooling coil, it is not a very easy business. Okay, it's a very difficult process. Modeling the cooling coil, it is the most difficult thing, because there will be lot of fins. Okay, so there will be lot of fins in the cooling coil. So when you are modeling the cooling coil, so it is going to be very difficult for you. Okay, so you are instead of that, what you can do is this cooling coil you can define like a domain. So there you can give that this much amount of energy is removed. So when you are doing that, so this will become negative. Okay, now you see it is very easy for you. So you need not model the cooling coil, meshing, and all these things you can avoid. Okay, and similarly, if you are having a heating conditioner, for example, in your room you are having a heater with a fan. Okay, so heating AHU. So there it is going to be plus value. So there what will happen? The cold air from the room, it will be entering into that conditioner. So there it will be gaining its heat. It will be receiving heat from the heating coil. So that means there I can give this S value as a positive. Okay. So from the energy perspective, you can understand this now. Similarly, you can have the source for this also. Okay, you can have the source for this also. So you think that you think even water vapor also, you think suppose if water vapor is going into the room, into the cooling coil, so what is happening to the water vapor? Water vapor will be reduced. Okay, so it will be losing the water vapor in the cooling coil. So what is happening? So you can put that as a sink. Okay, you can put as a sink in the air conditioner. So because of that, what will happen? So whenever air is flowing into that cooling coil, the water vapor will be absorbed. See, instead of doing a complicated thing, your source terms are helping you to reduce the complexity. Okay, So these are all the source terms. Okay, so the you can similarly there can be addition of moisture also. So in a heating coil or if you are doing an air washer, there you can add moisture to the room. So in that case, what you have to do? So you have to add the water vapor. So that means that will be a plus source. So all these things are possible. Okay, so all these things are possible. These terms are called as momentum. I mean source terms. So whatever I showed now, those are all the source terms. Okay, fine. So now we know about the transient terms. We know about the source terms. And yesterday I have introduced to you the convection terms also. Okay, so I have introduced to you the convection terms also. Okay, so what is how the fluid is flowing? Okay, so what is the how the fluid is flowing? What is the reason for the fluid to flow? Okay, that we have to understand. So the reason for fluid to flow is so this source terms. Okay, the source terms. Just now I told you what are all the possible source terms in the momentum equation. Okay, so this source, whatever I told you, adding, removing source. Okay, so all these things are there. X, Y, Z it is there. Okay, there are two other sources which are all responsible for the flow, for responsible for creating the flow inside the domain. So those are the things like I have a pressure gradient term. Okay, then I have the body force term. Okay, so this term is a pressure gradient term. Okay, so this term is a pressure gradient term. Okay, so and a pressure gradient is also a vector. It is appearing in the X, Y, and Z. Now all the three directions this pressure gradient terms are appearing. So that means how the natural question is how you are saying that. Okay, the natural question is how you can say that pressure gradient is source. Very important. Sorry, very simple that you think that high pressure air is there inside a tank. Okay, high pressure air is there inside a tank. Okay, compressed air tank you may be knowing. So just you open the valve. What is happening? Outside you are having atmospheric pressure. Inside you are having a high pressure. So because of the difference, flow is created. So that means the pressure difference can create a flow. So that it can work. It can help us a source term for creating the flow. So that is this term. So that is what I am saying. So if in a modeling zone, if you are having the pressure difference, so that can have, okay, depending on where you are having the predominant flow. So this you can have the X component of the pressure, Y component of pressure, and the Z component of pressure. Okay, that is how the pressure can appear in the source term. Similarly, how this rho G can have it in a source term. So what is rho G? Rho G, it is the body force per volume. So that is mg by v. Mg by v. Because in other words, mg, what is mg? It is body force or the weight per unit volume. Okay, so and what is the energy component corresponding to that? It is mg h. So energy, potential energy. You know, if you are pumping your water, which you are getting it in your sump, you are pumping the water to overhead tank. What's the reason? So it is like you are storing the energy. Okay, whenever you want, you open the tank, you are getting that. How this flow is created in the tap? This energy, the pumping energy only, it is stored in the tank. Okay, it is in the form of potential energy, mgh. Or you think about water which is available in the mountain, it is having energy. Okay, likewise in the house also, we are pumping the water to the overhead tank. So that is mgh. Okay, and the whenever you want, you can open the tap and you can. So that means what? So when you are storing the fluid, okay, at a higher altitude, okay, so it processes the energy. So that we call it as potential energy. The force corresponding to that, it is the body force. Mg is the body force. Here rho g is body force per meter cube. Okay, so now you can understand how this can work as a force. But for this, very important is that the density should be higher. Only if you pump water to a higher height, okay, that means pump water in a overhead tank, then water will come from there to your tap. If you are thinking of pumping air, okay, to an overhead tank, and if you are thinking of getting it in the tap, So you have to think of that. Okay, density is very important. When the body force will be more, only if density is more. For water, the density is 1,000. So that means the force is 1,000 times that of air. So that is why the body force is more. You are able to get it in the top. But if you are pumping air, density is 1 by 1,000 times. So the potential energy will be lesser only. So you will not have the sufficient energy to pump that. So why I am telling all these things, you should understand this. If this SMX is having three components. One is minus dou P by dou X, that is pressure gradient. Okay, flow can be created because of pressure gradient, and because of the body source term also. The flow can be created because of the body force term also. So it can be created because of the pressure gradient, or it can be created because of the body force also, or it can be created because of the external force like fan, okay, pump like this. Okay, so it is created. Now we have understood how the flow is created through the equations, and how this what this flow will do. So whenever a flow is created, this flow will do only two things. One is convection and the other one is diffusion. Okay, mostly convection is very known to you, so you will understand very better. Okay, convection is because if you are opening the tap water, convection is created. Okay, similarly, if water is flowing from the mountain, convection is created. Okay, similarly, you are opening the tank, that is a high pressure tank, compressed air tank, flow is created. So what you see immediately is the velocity. Okay, so that means these terms you are seeing these terms. What are these terms? So these convection terms we are seeing. Just excuse me, my thing is not working. So these terms are, you are able to see these terms, whatever I am having on the right hand side. Okay, so these terms, what I have it on the right hand side, so I am able to get. So what is the meaning of that? So the meaning is that, so whenever the source is there, okay, source for the fluid flow is there, naturally it will be ending with convection. Okay, convection. So how convection is created, just now I told you, because of velocity. So when the source is there, it will create velocity because of that momentum. Convection of momentum will be there. So what is convection of momentum? Convection of momentum is when the flow is created, along with that velocity will be increasing. So because of that, flow will be there. And the main thing is when the flow is there, yesterday we have seen that, so it will transport the property temperature from one place to another place. Similarly, when flow is there, it will transport the property species. For example, if you think that water is flowing from a mountain, so suppose the color of the soil is red, so it will take that property. What is that? It is actually a chemical. Okay, chemical, or how you understand. So that it will transport from the mountain top to the bottom of the. So that means whenever flow is taking place, this red color is added to the water. So what is that we understand about the fluid? So when a fluid is flowing from one place to another, wherever the property is there, it will take that property and put it in the next place. So that is what we call it as convection. So if it is taking the property temperature from one place and putting it in another place, so it is called as energy convection, okay, or heat convection. If it is taking the property species from one place to another place, so then we call that as a species conversion, or convection mass transfer. Okay, if it is taking the property of momentum, so then it is called as a convective diffusion. Convective momentum transfer. So in convective momentum transfer, only if there is acceleration or deceleration, these terms will be there. So this is very important. This please try to understand these terms. Okay, so this term, these three terms, whatever we are having, and these three terms, whatever I am having, and these three terms, whatever I am having. So this will be there only if there is acceleration. Okay, because when the flow is taking place in the nozzle, okay, so what is happening? The flow will be accelerating. Okay, so that means then only there will be a gradient of velocity. So this acceleration is not temperature time acceleration. It is convective acceleration. So convective acceleration is like a flow is happening in a nozzle or in a converged space or constriction. So nozzle means don't always think about a funnel shaped nozzle. This nozzle effect can be created by a converging building structure or converging tree structure or converging whatever the structure may be. So when the flow is happening from a bigger cross section to a smaller cross section, acceleration will be taking place. So that point only these three terms will appear. Okay, that point only these three terms will be there. If there is no acceleration, convective acceleration. Similarly, when these three, when there is a deceleration only, these 3 points will be appearing. So when there is no convective acceleration, and similarly when there is no convective deceleration, these 3 terms will not be there. These 3 terms will, three terms will not be there. Okay. So this is an important thing. Okay, this is what we have to understand. And what is that? If you just try to find out, so it's very simple. So what these 3 terms are telling? Okay, 1, 2, 3. So you would have studied about 2 type of losses in the fluid mechanics. So one is major loss, another one is minor loss. So major loss, it is because of the friction. It is because of the viscous friction. Okay, minor loss, it is because of the velocity variation due to acceleration in a pipe, reducer, bend. So all these things, okay, so minor losses, wherever you are having minor losses, these terms will be predominant, okay, because the minor loss, you know, invariably the velocity will change. So because of the change of velocity, if acceleration is taking place, that is called as a convective acceleration, okay. There is something called as a transient acceleration. That means a sudden rise in velocity because of time at a particular location. So that is that is because of this. Okay, so that is because of these terms. Okay, so this is how we call it as local acceleration. Okay, so these terms are convective acceleration. So convective acceleration is responsible for the minor losses. So that is what we have to understand. Okay. Similarly, now itself I will tell this term on the right hand side. Okay. So whatever I have a diffusion of momentum terms on the right hand side, those are responsible for the major losses. Okay. Major loss, I told it is because of viscous friction. Okay. So viscous friction means so you can term all the viscous terms are there in the right hand side only. Okay. So that means if you solve these things, okay, solve these equations, finally you can find out what will be the viscous friction inside there. So that is what we are doing. If you are going for a fluid mechanics, higher grade fluid mechanics, or you are going for a higher grade heat and mass transfer, you will be finding out what will be the drag coefficient, viscous friction coefficient. So all these things you will be doing. Okay, so that you do it only with the viscous terms. Okay, so that means that these terms are responsible for the major loss. Okay, so okay, what is diffusion of momentum? So whenever a fluid is there, there will be boundary layer. So from in the boundary layer, near the boundary layer, at the edge of the boundary layer, you will find that the friction force will be maximum. Velocity will be 0, but the friction force will be maximum. When from the lower edge of the boundary layer, if you are trying to move up in the upper edge, so what is happening? Your momentum, okay, your shear force is decreasing. Okay, so at the edge of the boundary layer, you will find that your shear force will be 0. So what is the meaning? When you go beyond the boundary layer, there is no viscous friction. Okay, inside the boundary layer, viscous friction is there. Okay, so in those places only, okay, so you'll be having viscous friction. In those places only, these terms will be predominant. So if you try to solve these equations, these terms in those places, you will be getting the viscous friction terms. Okay, so that means this will give the major loss. Okay, so that is what I told. This will give you the major loss, and the convection terms will give the minor loss. Okay. Okay, so now we have understood about the various terms in the equation. Okay, we have understood about the various terms in the equation. Just now, I think I've taken some time for you. I think, but this should be useful for you to understand the basics of equation. Not only here, wherever you go, if you are using this CFD equations, so these explanations and of equations, it should be useful for you. Okay. Now we will go back to our discussion. Okay, so now I have this general transport equation. So this is so I substitute these values. I get this various equations. I use it for CFD, and these are all the various equations. So just now we have seen. I have the transient components. I have the convection components, and I have the diffusion components. Okay. Similarly, we have a diffusion mass transfer also. Okay, so this is a diffusion mass transfer also, that is a spread of mass, okay, by diffusion. This is spread of mass by convection that I told you. Because of velocity, if some chemical is transferred from one place to another place, that is convective mass transfer. But if you, because of a molecular movement, if some species is transported from one place to another place, that is the diffusion mass transfer. Okay, so why I am discussing all these things, you should understand this is the basic structure of all the equations. So this is continuity equation, that is one physics. X momentum is one physics. Okay, y momentum one physics. Z momentum one physics. Energy equation is another physics. Similarly, if you have a, concentration equation, it is another physics. So if you are solving, if you go to discretization of your CFD problem, for a particular node, you will have all this equation. So yesterday when you have seen it, you are solved for energy equation only. So for that, one equation only you are getting. For energy, one grid you will be one equation only. But when you are going for a CFD problem, you will get all these equations. For that means for the same grid, for m plus 1, m minus 1, okay, or n plus 1, n minus 1 in 2D. So you will have all this overlapping physics. So that means you will have a continuity equation for the same node only. For momentum equation also will be there for same node. Energy equation also will be there for the same node, and the concentration also it will be there. Okay, concentration equation also will be there for the same node. So that is how you are going to have. Okay, so that is how you are going to have. So that means in CFD you will be having number of overlap in physics. But if you are going for energy simulation, okay, so you will be having mostly one equation, energy equation only. Similarly, if you are going for a FEA analysis, structural problem, so mostly you will be having force balance only, momentum equation only. Okay, but in CFD you will be having number of overlapping physics. So that means the number of equations that will be solved per node, it is going to be higher in CFD. So that means you are going to have memory problem. So that means you cannot go for solving by direct methods. Okay, direct method means inverse method and Cramer's rule. So those type of things you cannot use it in the CFD. Okay, in CFD, since you are the number of equations handled per node, it is very much higher. So it is better to go for iterative methods only. So then only you can solve the problem of memory. Otherwise, it is going to be a trouble. If you are going to have direct methods for CFD, definitely it is going to be trouble. Okay. Okay, so I think these discussions, we will go back to our CFD. Let us see whether it is converged. Okay, just 1 minute. Yeah, so now it's very beautiful. So now you can see the residue has come down. Okay, so the residue has come down for all the equations. Now what is that you are finding? The x velocity for the particular location, it is constant. So that is what we want. Okay, if the velocity is fluctuating, when the residue is high, you are finding that the velocity fluctuation is very much higher. What is the meaning? It is erroneous velocity. Okay, it is erroneous velocity. But as I am reducing the residue, what is that I am finding? I am finding that my solution is improving. So that means after this point, okay, my velocity is remaining constant. So that means we have obtained the convergence, velocity convergence. Okay, so now I think we can go and see the plot. Okay, so I'm just pausing here. Okay, so it is saying that it is not converged, but I'm because I'm seeing a constant velocity, I'm taking that the velocity is converged. I mean, the solution is converged. But all these equations should go less than 10 power minus 3, then only it will show convergence. But from my understanding, okay, I'm saying that okay, I'm getting constant velocity, it is converged. So then I'm going for the solution. Okay, now I will go and see the plot. Okay, 1 minute. So now you can see the domain. Okay, so are you able to see that? So this is the outer domain what we are having. Okay, so this is the building. So we want to know what is happening into the when air is flowing outside the domain. So what for that I have taken a very big domain. Okay, so this is so the flow is happening. Okay, so the velocity flow is happening here like this. So what is the effect of the flow on the building? So that is what we have to see. Okay, now from here you can see. Okay, so this is the direction. Okay, so this is the direction. So this is the direction of the building. Okay, north direction of the building, and the velocity flow is in this direction. Velocity flow is in this direction. Now we will see the plot. Okay, 1 minute. Okay, now before that let us. Okay, so we will see some plot is we are able to obtain some plot here. Okay, but we will be interested in finding out what is the velocity plot. Okay, what is the velocity and the pressure plot here. Okay, are you able to see that? It's a little bit slow. No problem. 1 minute. I want all of you to see this properly. Okay, I think it is not. Okay, no problem. We will go for the variable setting. So I am going for slice setting. Okay, in that the best for you to see is the best one will be. I don't think you can see the vectors. So this is the field pressure contours. Okay, so that is what is given here. So you can see the field pressure contours here. Okay. Little bit slow. Okay. Okay, I think this location will be okay. So I'll put the slice here. Okay, and I'll put the my flow is from this direction to this direction, so it is better to put one more slice here. Okay, you will be knowing why I am putting it here. Now I will rotate to see that. Okay, so yeah, here you can see the flow is in this direction. The velocity, the building is like this. The velocity is the flow is in this direction. Okay, from the left to right. So here you can see on the front side of the building there is a pressure rise. We call it a stagnation rise. So because of that stagnation rise, the air is coming with some velocity. It is hit by the building. So because of that, the pressure rises on the front side of the building. Okay, and on the rear side of the building, you will find that the air quantity will be less. So the wake will be formed. Okay, so there will be a diversion here, and the wake will be formed behind the building. Okay, so because of that, we will be having a low pressure. Even the velocity also will be lower here. Okay, so yesterday I told you. So now let us see the velocity contours. I want to enlarge this, but I am not able to do that. Some problem is there with this thing. Okay, the system. Maybe since I am online. Okay, so there is some capacity problem is there in the system. Okay, I will. Yeah, so I will remove all the slice, and now I will put the slice for velocity. Now I will put it in this. Okay. Uh, okay. So because I want it in this direction, because my flow is from left side to right side. Okay, my flow is in the left side to right side. Okay, 1 minute. I will remove this. Now you can see the plot is, if here the velocity is inlet is there here. So as it is approaching the building, because here it is the flow is being blocked, here the velocity reduction is there. So that's why pressure increase was there here. That is Bernoulli. Yesterday I told you Bernoulli. So since velocity reduction is there, pressure rise is there here. So that is Bernoulli. And here you can see the flow is accelerating above. Okay, the flow is accelerating above. So almost the velocity is uniform. And the rear side I'm having the wake. Rear side of the building I'm having the wake. Okay, and the wake is the place where you will be having low velocity as well as low pressure. So it's a low energy region. Okay, so that is how we have to understand. So and now I am getting the pressure distribution and the velocity distribution. Okay. So what are all the equations we have solved? So I have solved the continuity equation, momentum equation. So from that I have to get the pressure and velocity distribution. Velocity I should get it in the 3 direction. So in advanced solvers you can actually go and see all the velocities individually. You can see that. Okay. So here we are seeing the component of the velocity. Okay. So I'm seeing the velocity vectors. We are seeing the velocity vector here. Okay. So that is what we are seeing it here. Okay. Okay. So this is the external flow in the building. Okay, so if you want, we can see one more thing also. I think, okay, before it opens, we will go for our back to our discussion. Okay, so we will go back to our discussion. Okay. Okay, now that we have discussed about the equations, even discretization also we have discussed in detail. Today we have discussed about the equations. So similarly, what is that we have to understand about the boundary condition? If I have your domain, now you have seen a domain. If I have your domain, how many physics are there? So many number of equations will be there. That is what you have to understand. Similarly, how many physics, how many equations are there? So many boundary conditions will be there. For example, if I am having a continuity, so that means for continuity, I have to give separate boundary conditions. For example, in the solver, we will be giving a pressure correction boundary conditions. Okay. Similarly, for momentum, I have to give boundary condition for x velocity. Similarly, I have to give boundary condition for y velocity. Similarly, I have to give for z velocity also. Okay. So that is what we have to understand. So that means for each equation here, I have to give the boundary condition. For the same node or for the same volume, for each equation, I have to give the boundary condition. Similarly, thermal boundary condition also I have to give. Similarly, concentration also, species concentration. If you want to give, that also I have to give, okay, individually. That is how I have to solve the boundary condition. So yesterday we have seen a boundary condition. It can be a prescribed variable, that is phi. Phi may be what? It can be velocity, it can be temperature, it can be concentration. Or we can give the flux form of phi. That is the differential of phi. Okay, that in that form also we can give it. So that is called boundary condition of second kind. Or we can give both together. So that means we can give phi as well as dou phi by dou x, both put together. So that is the boundary condition of third kind. So here that means the unit may not be matching. So for matching the unit, we will be bringing at h. Okay, we call it as a heat transfer coefficient. Like that will be mass transfer coefficient, similarly momentum transfer coefficient, like that we can bring it. So that means 3 types of boundary conditions are there: prescribed variable, prescribed flux. Okay, all these boundary conditions can be given. Okay, so this we have to give. Yesterday we have seen about thermal boundary conditions. So likewise, you can give in momentum boundary condition. We can give species boundary condition. In momentum boundary condition, most important is no slip condition. So that is near the wall, velocity will be 0. So that is called no slip condition. U is equal to 0, V is equal to 0, W is equal to 0. So that is a boundary condition of first kind that we have to understand. Like that, several important boundary conditions are there. So what is that we have to understand is for each equation, we have to give the boundary condition. So that we have to understand. So different types of boundary condition. Just now I told you. So this is prescribed phi, prescribed flux, and this is both put together, prescribed. So it is technically it is called as Dirichlet conditions. Prescribed phi is called Dirichlet condition. Prescribed flux is called a Neumann condition, and prescribed both put together it's called Robbins condition. Okay. So all these boundary conditions you can give. Okay, very good. So this the domain will be looking like this. So it can be regular like this, or it can be uniform grid. Okay, it can be a non-uniform grid like this. Okay, and how so in the finite volume method. Okay, so yesterday we have seen about finite difference method. In finite volume method, how we are going to solve these problems? In finite volume method, we are going to solve these problems by integration procedure. So that means how same thing in finite difference method, we are finding the algebraic equation for the partial differential equation by finite difference method, that is by Taylor series. Yesterday we have seen that. Here what we will be doing is in finite volume method, we will be finding the same algebraic equation by integration of the governing equation in the domain. So the integration of the governing equation in the domain, so it is done. Okay, you know, after the integration, what is that you will go. So if I am doing a volume integration, so you should know the first limits of integration will be points. Okay, the second limits of integration will be lines. Third limits of boundary conditions will be areas. That is how in a volume problem you will be having. So that means finally everything should end up with points only. So that means it will end up with the grid points only. So that means you will get the term like what you have got yesterday. So what is that you have got yesterday? T1 plus T3 minus 2T1 is equal to 0. So this is an algebraic equation. So even you do integration also, you will be getting like this one. Okay, almost same equation you will be getting in finite difference method or finite volume method. You are going to get the same information. Then why we are going for finite volume method? We are going for finite volume method because it is very easy for us to handle the complicated volumes, but that is difficult in finite difference method. Okay, so that's why we are going for finite volume method. But the basic ideology is the same. Okay, so the same volume, same discretization, we are converting the equations into algebraic equations. The solution, all these things are same, but we have the convenience of handling the geometry in finite volume method. Okay, okay, so this is how we will be having cell structure in the finite volume method. Okay, and usually in finite volume method, we will be giving the grids in this form. You will be giving the grids in this form: east, west, north, south. Okay, and how we will be going for discretization. Yesterday we have seen how we are going for discretization, but there we have seen only diffusion term, only conduction alone we have taken, transient conduction. That means you have taken this term and this term alone plus source term. That is what we have done. But now convection term also you have taken. So how you are going to solve this? With the diffusion term, the discussion is very simple. But when you are taking convection also, okay, then it involves. Okay, so how we are going to solve? So here we are just taking C instead of phi, our variable. I am taking C. So that means it can be velocity, or it can be temperature, or it can be species concentration. For everything, the discretization procedure is same. But that is why we are taking just only one thing, which is called as C. So this side I am having east, this side I am having west node, and this side. And in finite volume method, we will be storing the values at the centroids, okay, cell centroids. And when I am going the discretization of this equation, discretization. So this equation, it is given in the tensor form. I means it is there in x. I can be in x, y, and z. Similarly, here also it is there. So that means this is a general transport equation in the 3-dimension, but it is given in the tensor form. By seeing this, you have to remember that equation. Okay, whatever we have seen previously. Whenever so you consider a 2-dimensional domain, so we do a sample discretization just for the sake of understanding. So if I am doing the thing, so left hand side, okay, so what is that we are assuming? Source is 0, and I am putting a transient. It is not transient, it is steady state. So that means I have a convection diffusion equation. I am taking only 2D only. So that means Z component I am neglecting on both the sides. So that means I will be having dou U by C by dou X plus dou U C by dou Y. Similarly, I will be having dou by dou X of dou C by dou X. Similarly, I will have dou by dou Y of D dou C by dou Y. So these terms are there. When I am going for discretization, I am going to have it like this. So this is the cell. For this I am writing, like we have seen yesterday, the flux value at the east minus of flux value at the west. Okay, I am doing the integral of this equation. Okay, integral of this equation. So I will be having flux at east minus of flux at west. Similarly, flux at north minus of flux at south. Okay, plus okay, source term is also there. Take it, no problem. Similarly, next I am going to take the this term. Okay, first order integration. So when I do the integral of this, I will be having AUCE at east minus AUCE at west. Similarly, A, B, C, N, because this is y direction, we have ns. Okay, similarly, velocity will be v velocity. So A, B, and C, N minus of A, S, C, V, N. Okay, that's how. By seeing these two things, okay, this you know, yesterday we have seen how you can do this. East means CE minus of CP divided by delta X. Similarly, west means CP minus of CW divided by delta X. North means it will be CN minus of CP divided by delta Y. Similarly, here it will go in CP minus of CS divided by, very sweet. Right hand side, there is no, absolutely no problem. But here, left hand side, this will be looking like simple, but this is where the trouble will be there when you are going for a convection diffusion problem. That is actually in CFD problems, when you are going for CFD solutions, left hand side only you will be having problem. Okay, why you will be having problem? Because you are going for interpolation of U, because U is, you are taking at the wall, east, west, north wall and south wall. But in reality, U is not available at east, west, north and south. It is available at the centroid only. So then how you are going to take the U value at the face? By interpolation. So because of that interpolation only, we will be having trouble. Okay. So this is the general discretization. Okay. So what are all the possible discretization? So the simplest form of discretization, what you can have it for the UE is, I can take average of this. I can take UE plus UP divided by 2. Okay. Similarly, for a W, I can UW, I can take U P plus UW divided by 2. That is how I can take it. If I take like that, so that is called the central difference discretization. It is most simplest form. Okay. So it should work. Okay. So central difference discretization. So we are taking it is most simple form. It should work. But when you are going for highly convective flow, not highly convective flow, even small convective flow with the higher velocity, then you will have trouble. Because if you are going for central difference discretization, for lower velocities, it will work without any problem. But for higher velocities, there will be trouble. Because the discretization scheme, what you are having, okay, it is central difference scheme. It is transporting the information equally in all the directions. For example, if you are taking average of this, you are giving equally here. This plus this divided by 2, you are giving equally here. Similarly, if you are doing here, you are giving equally here. Similarly, on the north, you are giving equally here. Similarly, in the south, you are giving equally here. So that means you are taking the values, okay, equally in all the directions. So that means there will not be, that is like diffusion. Because yesterday I told you about the diffusion. So diffusion will give you information equally in all the directions. But what is that you are taking? The physics is convection. For convection, if you are giving the diffusion physics, will it work? It will work fine at lower velocities, but higher velocities it will give trouble. But for CFD problems, mostly you will be having a highly convective flows only. Okay, so even a problem with the high velocity, it will be like a highly convective flow. So if you are going for central difference discretization, then left hand side you will be having trouble. So what you have to do? So you have to go for a different type of discretization. So that is what we have to discuss. Okay, so you can arrange all these things and you can go. So now if I am going for this discretization, central difference discretization, just now what I am discussing, at low velocities I will not be having problem, but at high velocities I will be having problem. So what is that high velocity, low velocity? So I have to tell that in terms of Peclet number. So Peclet number, it is the ratio of convection to diffusion. What is convection? If high velocity flow, it is like rho u. Rho u represents convection. Okay, d by l it represents the diffusion. That means if the ratio of convection to diffusion, if it is less than 2, you can use for central difference scheme. If the ratio of convection to diffusion, if it is greater than 2, if you are using central difference scheme, it will give unstable results. Very important, unstable results. So that means your scheme will not be working. Okay. So what is the remedy for that? Okay. The remedy is just you think in terms of natural. Natural thing is highly convective flow, you go for convective discretization. So how I can do that? What is that I have to understand? If there is a grid, okay, so if I am going from left to right, okay, flow is there from left to right. So this is the x-axis. You think that flow is there from left to right. So what is the meaning? The velocity information, velocity inlet I will be giving here. So that means information is present on the left hand side. Okay. and right hand side you will not have the information. So that means when you are going for solving the problem, this left hand side information it should be transported immediately. If you keep on giving it equal in all the directions, so that means there is some trouble in your discretization. What you have to see that is that left hand information, it has to go immediately to down the line. So that means, for example, if you are having high velocity here, so this high velocity information should go down the line immediately. So for that, what you have to do is you have to go for uppoint scheme. So what uppoint scheme does is you take any phase, it will take the uppoint value only. Just it will take the uppoint value. It will no averaging business. For this phase, it will take the uppoint value. Similarly, for this phase, it will take uppoint value. For any phase, just it will take what is there at the left hand side. Now, what is the advantage of this? Your information, velocity information is there at the left hand side. You are giving priority to that left hand side. So because of that, what happens? Your information, velocity information will go into the domain immediately. So that means your scheme is good and it is safe. Okay. So that is what we call it as first order uppoint scheme. Okay. So that means at higher velocities, okay, or highly convective flow, at higher Periclet number, you have to go for first order uppoint scheme. Okay. So you can go for improvement of first order uppoint scheme. Okay, you can use exponential law. So in a exponential solution, or you can go for power law scheme. In a power law scheme, what is that you are understanding? You go by exact solution method. The exact solution for convection diffusion, it is exponential. So that means you have to do the discretization like exponential problem. So that means you do the interpolation of an exponential. Okay, in the node under consideration, it is P, and on the right hand side, I am having E. So I do the interpolation as per the exponential. So that means phi E will be this term, phi P minus of this. How you are getting that? By interpolation of exponential. That is from the exact solution. So that also, it helps me in handling the convection. So that means for Periclet number greater than 10, I have to go for uppoint scheme. Less than that, I can go for this scheme without any problem. Okay, so that means this scheme is capable of handling this convection trouble up to Periclet number 10. Okay, and greater than that, this scheme also it is having problem. Central difference scheme, it is capable of handling up to Periclet number 2. Power law scheme, it is capable of handling up to Periclet number 10. And beyond Periclet number 10, again you have to use the first order uppoint scheme only. And for first order appointments, in the name itself it is there, first order error will be there. First order appoint means first order error will be there. For avoiding that, what you can do, you can go for second order appoint scheme. That means for this interpolation, I'm not giving the formula. For the interpolation here, I'm using two terms on the appoint. Previously, I am used only P. Now I am using a W also. So that means I'm using two terms on the appoint. So if I do like that, that is called second order appoint scheme. So this will be more accurate compared to the first order appoint scheme. Okay. Similarly, even you can go for the quadratic. Okay, which will be using the three nodes. So the three nodes you will be having using west. You will be using the node volume under consideration and even the east value. But the weightage will be higher for west P and the least will be for phi P. Okay. Phi E will be this quick scheme, this interpolation scheme. It will be very good, accurate. But if you are going for higher velocities, so there will be in the radians, in the areas where you are having strong gradients, you will be having overshoots and undershoots. Okay, so that will create trouble for you. So that means you have to go for limiters. Okay, for avoiding this problem, you have to go for limiters. So that is a separate, very big topic. Okay, but what you have to understand is quick scheme can be used. But if you are using quick scheme at in the places where higher strong gradients are there, we will be having undershoot and overshoot errors, which will be there. Okay, so now you know that our discretization scheme will be like this. Okay. Right hand. Okay, so we know how to handle the diffusion term. We know how to handle the convection term. In convection, if I want to consolidate in convection, left hand side. Okay, in convection, left hand side, I'm having the convection term. There only trouble is there at low velocity. There will not be any problem. Central difference scheme itself you can use it. But if Periclet number is 2, that is at higher velocities, trouble will be there. I have to go for upwind scheme. if I am using the your power law scheme as well as second order upwind scheme or quick scheme, I can handle this convection problem without any trouble. But in the area of high gradient, I will be having the problem of undershoots and overshoots. So that I have to handle. Okay, so in all, okay, when I want to conclude, okay, so how it is, my overall discretization scheme is like this only. Okay, AP phi P is equal to AW phi W plus AN phi N plus AN phi E ASIS plus B. So this I can write it as summation of neighboring nodes plus B. Okay, so all of you hear very carefully. So if you want to understand CFD or numerical or anything, okay, so here is the important information. Okay, here is the important information. So that is, you can write, okay, so you can write this discretization also like how you wrote in the general transport equation. So that means the general transport equation, you had it like this, no? So that means you had one equation, okay, you had one equation. So from that, okay, so you derived various equations, 1, 2, 3, like that. We had various equations, okay. Likewise, in discretization also you can have the various equations. So that is what is given here. So after this discretization, we should understand that even in discretization also I have a general form. So that this algebraic form, I can have it for even continuity equation. In continuity equation, phi p will be in a pressure correction form. In the momentum equation, phi will be what? U velocity. In the y momentum equation, this phi will be v velocity. In a z momentum equation, this phi will be in a w velocity. And in the energy equation, the phi will be t. The same form only. And in the species transport equation, the same thing will be, the phi will be in a concentration. If so like that it will go. So that means even this also it is very simple for you. You can understand. So even algebraic equation also it is in the same form only. Okay, so that is what you have to understand. And the next most important thing, okay, next most important thing what you have to understand is very, very important. So you can see the node under consideration, it is connected to the neighboring nodes. Okay, so the node under, even in the, that you can see, even if it is in the matrix form also, it is connected to the neighboring nodes. So this is node 1 equation, node 2 equation, node 3 equation. So node 3 here you can see, this is a node under consideration, 1, 2, 5. These are neighboring, this is not neighboring. So that means 1 to 5 coefficients are there. 1 to 5 coefficients are there. So that means everywhere in the equation, whether you go by FDM or you go by FEA or you go by CFD, all the nodes under consideration or volume under consideration, it is connected by the neighboring nodes. Okay. What is the significance of this? If I take a one-dimensional problem, okay, you know, all the nodes are connected. All the nodes are connected. Okay. If I have a one-dimensional problem, you know, it is like a wall. Left hand side I will be getting the boundary condition. Okay, left extreme and the right extreme I will be having the boundary condition. Since all the equations are connected, the left side, if I give some information, for example, in this matrix, you mostly one-dimensional problem, you will have boundary condition here and here only. So that means what is happening? I give the boundary condition here. That information it is given throughout. How the information is going? Because it is connected. Left hand side, for example, one-dimensional problem. Yesterday we have seen in an equation. So for if I am writing for node 2, the equation will be like this: T1 plus T3 minus 2TT is equal to 0. So that means T1 left hand side is there, right hand side is there. Okay. Similarly, if I am writing for 3, so it is going to be T2 plus T4 minus 2T3 is equal to 0. So that means always neighboring nodes are there. Okay. That means these neighboring nodes are transferring the information. In a one-dimensional problem, it can transfer the information only along the line. Okay, that means from the left it can give to the right. Okay, so that is how it is connected. Okay, physically also it is connected. So at the left hand side you give some information, immediately it will be transported. Similarly, if you take a two-dimensional problem, in a two-dimensional problem, it is not only connected in the left and right, it is connected at the top and bottom also. Why? Here we can see. Okay, here you can see. So it is connected to east, west, and also north and south. So that means the node under consideration, volume under P, it is connected at east, west as well as north and south. So that means if I have a two-dimensional domain, okay, in somewhere on the left side of the domain, or the right side of the domain, or the top of the domain, or bottom of the domain, If I give some information, this information will be transported equally in all the directions. So that is what this equation is telling. So that connectivity in two dimension, it is there on the left hand side, right hand side, at the top and the bottom. That is existing in algebraic form. Even in the matrix form also it is existing. That is what you have to understand. Similarly, for three-dimensional equation also the same thing is applicable. So in a three-dimensional equation, the equation not only connected with the east west, north south, okay, it is also front to back also it is connected. Okay, so that means here I have to add, so east west, north south, then front to back also I have to add it. So then I'm going to have 6 terms on the right hand side, okay, left hand side. So that means what? It is connected throughout. So that means in a three-dimensional domain, that is a volume. So you will be giving the boundary condition on the east face, left face, east face, west face, north face, south face, front face, back face. All the information is going to get it transported. So that means what? Because of this connectivity only, all the informations are getting transferred. What is that information? Information what is available at the boundary, it is getting transported inside. In a one-dimensional problem, the informations are available at the end point. Okay, it is getting transported inside. Similarly, if you are going for a two-dimensional problem, the informations are transported available along the lines available at the boundary. Okay, so those informations are transported inside. If you are going for a three-dimensional problem, these informations are available along the area. Okay, so these informations are transported inside the domain, inside the volume. Okay, how it is transported? It is because of this mesh connectivity. You understand this mesh connectivity problem, it is very simple for you to understand the numerical method as well as CFT. Okay, so with this I will stop. Okay, so maybe tomorrow we will continue our discussion with the iteration procedure. Okay, so we will go back to C. Okay, I think the time, it is almost time. We will go back to C. Yeah, so I just will see this 3D building, and then we will leave. Okay, just 1 minute. So now we have seen only one building, no? But usually when you are going for analysis, so you may be having a 3 or 4 buildings, okay, scattered. Somehow it will be there, okay. So I've just taken 3 buildings, okay, and we can do the analysis, okay. So we can do the analysis for that also, external analysis for that also. I'm not going to take so much time, just 2 minutes or 3 minutes I will complete, okay. Please don't worry. Within exactly at 8:10 I will complete, but the computer should open before that. Yeah, fine. So for this also, I am giving so think that some few buildings are there in the street. You are interested in finding out. Okay, so already the solution is available. Okay, no problem, and that means it's very simple for you. I can complete much before that. So now here you can see this is the top view of the building. Okay, so this is the top view of the building. The air is I have given the boundary condition here. The air is entering here in this direction. Okay, and it is hitting this building, second building, third building. Okay, so first building it is getting affected. You can see more pressure rise is there. Second it is less, and similarly the wake behind the first building it is higher. So in all this you can find that the if it is like a multiple buildings, in the front side and all you will be getting a good air. Okay, rear side and all air circulation may not be there. Okay, so that is the one thing what you can understand. Similarly, 1 minute, I will go for slide setting. We'll see the velocity distribution also. Okay, we'll see the velocity distribution. So I have the pressure contour. I will put a velocity, field velocity contours. I will do that. Okay, then I will remove all the slides. Okay, now I will give the slice for this, and I want it in the vertical direction. Okay, I will move. Now you can see it's okay. It's very good to watch. Okay, now yeah, here you can see flow behind the building. I told you about the wakes. Okay, you can hear this arrow. Okay, so that red arrow it is telling about the flow. The flow is in this direction. Okay, I put in some 15 meters per second, and here you can see something interesting. You can see so the first building wake is here, second building wake is there, third building, the wake is separate and air is able to move inside. Since I am giving a gap, a higher gap, air is able to move inside. So that means if you are constructing the building like this, you can do the analysis. So you should make the air to move inside the building. Then only ventilation will be there. If you are having two buildings closer like this, okay, you can see the air is not moving inside. So that will be like a hot pocket. So pressure will be less. Okay, so the ventilation, air circulated will be less. So then I think you should avoid closer buildings. Okay, closer buildings like this you should avoid. Okay, so like that you can do it. You can do it for a complete street also. So when I started, okay, my discussion, I showed some cities. They have done for some cities, some streets, big streets. Okay, so that is how it is going to be. So today we have discussed about the external flow analysis only. Okay, so you have discussed about external flow analysis only. So because of the lack of time, okay, I stop here. Okay, I will stop here because whatever I told, I discussed in detail. So that is why it has taken time. Okay, I think it is exactly 8:10. I will stop here. Okay, so I will stop here. Balance things we will discuss tomorrow. Only 4 or 5 slides are there, so that we will discuss tomorrow. One important thing I want to tell you, tomorrow you are having a session. Okay, tomorrow you are having a session. It is like whoever want you can attend. So that session is for heat transfer in glass and energy conservation. Heat transfer and energy conservation in glass. Glass, by using glass, how you can conserve energy, or what is the principle of heat transfer in glass. So that is what we are going to discuss tomorrow. So tomorrow, whoever interested, you can attend. Okay, so I'll be happy even if 10 or 20 are there. It is okay for me. Okay, so you can attend tomorrow. So tomorrow is Sunday. Tomorrow it is optional. You come or you don't come also, no problem. But I have a session on heat transfer and energy conservation in glass. Okay, so if you want, you can come. Okay, that is one. And the next thing is, if you have any doubt on today's discussion, you can put it in chat box. Okay, I have completed my discussion.
Sir, this is Ashok Kumar.
Yeah.
Thank you very much, sir. It's a high level and energy simulation and CFD class. Today I couldn't join. I joined very lately. May
Yeah.
I get PPT of this, sir?
Yeah. You will get
Sir,
PPT. If you want, you can get video also. No problem. Okay, the recording is there. No problem.
record. Thank you very much, sir. Thank you very much. Thank you very much, sir. Overall, you are
Yeah.
taking very useful classes. I'm glad to know about it.
Yeah. Yeah. Thank you. Thank you so much. Yeah, I'll post all the PPTs. No, don't worry. All the PPTs I will post because I was busy with a few things I could not do. All the PPTs will be available. Okay. In fact, we are planning to give all the videos also. So I think absolutely there will not be any problem. Okay. Especially for those who are attending regularly, it should not be a problem for you. Okay. So I think there is no question. Okay, so that means we'll do one thing. Tomorrow we will have a discussion. Okay, so it is like yeah. Tomorrow we will have a discussion. Monday we will continue with our CFD discussion. Okay, so tomorrow it is optional. So those who want, you can attend. Okay, same timing only, 6 o'clock. It may be a short session. It may not be like a 2 hour or 2.5 hour session like today. So it will be exactly 1 hour session only. It will be for glass. We have discussed about heat transfer in wall. We have not discussed about the heat transfer in glass. Okay, and something interesting is there in glass. So that is what we are going to discuss tomorrow. It will be definitely 1 hour session only. Okay, so those who want, you can attend. Thank you everyone for joining. Okay. Yeah, I'm completing because no question is there. I'm completing my discussion. Thank you very much.
Thank you very much, sir.
Yeah.